the final lecture in this mini course. In this last video, I'm going to be discussing the equality case of the positive mass theorem, or what might sometimes be called perhaps like the strict positive mass theorem or strictly positive mass theorem. So first I'll state the Riemannian version. So the Riemannian strictly positive mass theorem says that any complete asymptotically flat Riemannian manifold with non-negative scalar curvature has positive ADM energy unless it's Euclidean space. So remember the regular version, the non-negative version, just says E is greater than or equal to 0. Now we know that E is greater than 0 with the one exception of Euclidean space. So this was first proved by Shane and Yao, and they proved it was a consequence of knowing that the corresponding non-negative mass theorem holds on all nearby metrics. So therefore, you can think of it, the proof that they use is variational in nature, and it depends on knowing that you are at a local minimum for the ADM energy. So you can also think of it as a rigidity statement. It's saying that in the case where E equals 0, you have to be Euclidean. So I started off talking about the Riemannian version because the initial data set version is a little more complicated. The version for initial data sets is trickier because it's not quite a rigidity statement. If the inequality becomes an equality, you don't know exactly what initial data set you have, but you do know something important about the initial data set. So to explain why, notice that if you have any asymptotically flat space-like slice of the trivial Minkowski spacetime, all of those slices will have the equality E equals length of P equals 0. So that means that the initial data sets enjoy some degree of flexibility, right? You can take perhaps a flat slice of Minkowski space, and if you deform it, as long as you're deforming it within Minkowski space, you'll just keep getting more and more initial data sets, all of which have the exact same ADM energy momentum. And of course, they will also all satisfy the dominant energy condition. So the correct statement for the equality case, right, is not that you know that you have trivial initial data, but rather just that initial data is coming from Minkowski. So for physical reasons, right, we expect that these examples coming from Minkowski are the only examples with E equal to length of P, and that is the theorem. So here's the statement. It's a strictly positive mass theorem for initial data sets, says that any complete asymptotically flat initial data set satisfying the dominant energy condition must have future time-like ADM energy momentum. So that means that E is strictly greater than P. So remember the version that we had from last lecture, the regular non-negative mass theorem, just says that it's the ADM energy momentum is future causal. Now we know that it's future time-like. So we know that not just that E is greater than or equal to P, but that E is strictly greater than P, which would mean that the mass that we defined in the last lecture, right, the mass would be strictly positive. But we won't talk about the mass. We'll just talk about the energy and momentum. So that's the case. You know that that's true unless mg isometrically embeds into the Minkowski spacetime with K as its second fundamental form. So in that sense, you can think of the initial data as coming from Minkowski. So for convenience, I'll refer to this as being MGK sits inside Minkowski so I have a way of referring to this fact of isometrically embedding with K as your second fundamental form. So Shane Yao's Zhang approach in 1981 proved that E is strictly greater than 0 unless MGK sits inside Minkowski. So at least we have a strictly positive energy theorem at this point. Although there is an extra assumption that the trace of k has to decay faster than r to the minus 2 to make this argument work. And that assumed decay is actually not particularly desirable, but it's an artifact of the way the analysis works in that proof. Now, Witten's spinor method implied that if mgk sits inside a spacetime satisfying the spacetime version of the dominant energy condition, which we discussed a little while back, 2 lectures ago, I believe, then again E is strictly greater than 0 unless the ambient spacetime is flat along M. Okay, right? Minkowski space, of course, is flat, so this is saying that again the ambient spacetime is flat along M. But again, it assumes again, the conclusion is only that E is strictly greater than 0. So those results left open the possibility that you could have a situation where E is still greater than P, that E is still equal to P, but both of them are strictly greater than 0. So those theorems do not directly eliminate this possibility. But that was the conjectured statement, and that was proved eventually by Baig and Kruschel in 1996, and they used spinors to give the first full proof of the strictly positive mass theorem for initial data sets. So more recently, Lan-Xuan Huang and I gave a proof that does not depend on spinors, but instead uses a variational principle. So all 3 of those proofs that I described on the previous slide, they rely on the actual method that is used to prove the non-negative mass theorem, or perhaps the non-negative energy theorem. And in that proof, they check what happens when you have equality. So what we wanted to do is we wanted to give a proof that was sort of that was variational in nature, and most importantly does not depend on what method you use to prove the non-negative mass theorem. In other words, we just want to assume that the non-negative mass theorem is true and then obtain the strictly positive version as a consequence of it. So this is analogous to what Shane and Yao did in the Riemannian case. Well, the core result is the following. So, but we didn't quite actually go all the way, but we did this situation, which is the sort of a big part of what needs to be done, is that we proved that if mgk is a complete asymptotically flat initial data set satisfying the dominant energy condition with the equality E equals length of P, and if we assume that the non-negative mass theorem holds for all nearby initial data sets, then the energy and momentum have to be 0. Well, once the energy and momentum are 0, first let me point out, why did I put this little star above the asymptotically flat and make it in red? I just want to point out in both our paper and in by Kruschel's paper, we actually need a slightly stronger definition of asymptotic flatness. So it's just like a technically stronger, so most people wouldn't necessarily see this as that different. So I put in red the differences between this sort of stronger version of asymptotic flatness and the one that I introduced in the previous lecture. So basically it's asking for not just the first 2 derivatives of G to have appropriate decay, but also the 2 plus alpha Holder derivative to have good decay. Similarly for K, just again an extra Holder derivative. The main big difference here is the difference for mu J. So again, we want a little bit of Holder decay on mu J, but the decay rate that we want is exactly the one, basically what's the decay rate needed to imply integrability. Okay, so that's certainly stronger than just assuming mu and j are integrable. Okay, and the Holder exponent actually, the way I've formulated it, has to be at least 1/2. Okay, so that's our asymptotic flatness. So the comment I was going to make is, why is this good enough to, well, good enough to prove that we're in Minkowski? Well, once you know that E equals P, E and P are both identically 0, then we can use Shane-Yao's strictly positive energy theorem, the one that says that if E equals 0, then it's in Minkowski. And so now we get an alternative proof of the strictly positive mass theorem. When I say alternative, I mean it's an alternative to Bayes and Kruskal. So Bayes and Kruskal, theirs uses spinners, and ours is a combination of this new theorem plus Shane-Yao's theorem, which used the Jang equation. Again, because that part of the argument, again, will assume some decay on trace K. Okay, so one reason why we wanted to do this is, again, since it's not a new result in 3 dimensions, is that in higher dimensions it is, because in higher dimensions, right, the Bayes-Kruskal argument can be extended, and it was extended by Kruskal and Martin, to spin manifolds of higher dimension. But what about non-spin manifolds? So we wanted to have a theorem that works for non-spin manifolds as well. So the theorem statement here is the same statement that I had before. I just want to point out that although everything, again, for the most part in this series of lectures, I've been focusing on 3 dimensions, I just want to say that this theorem does work in all dimensions. So as I said, it still holds in higher dimensions, but it's important to point out that in dimensions n greater than or equal to 5, we actually need a stronger decay rate than the usual one. So in the standard assumed decay rate for the typical non-negative mass theorem is usually that Q is greater than n minus 2 over 2, where n is the dimension. It turns out that that's not quite good enough for us to prove our theorem, so we actually need Q to be strictly greater than n minus 3. And again, that sort of decay rate assumption also appears in the work of Kruskal and Martin in the spinor case. All right, so why am I making a big deal out of the decay rate? Well, in high dimensions, Huang and I also found counterexamples of complete asymptotically flat PP wave initial data sets that actually satisfy the dominant energy condition and have E equal length of P strictly greater than 0. So the naive conjecture would say that this shouldn't happen, but it turns out that we can find them, but they're not. The examples are not so radical in the sense that the asymptotics for these are poor. They're poor in the sense, well, they don't have Q greater than n minus 3. So that's good, because that means it doesn't contradict the theorem above. Okay? But they do have Q greater than n minus 2 over 2. So these examples of these PP wave examples, they still lie in the class of spaces for which the non-negative mass theorem holds. But we now see that the strictly positive mass theorem doesn't hold on this class of decay rates. So that was a little surprising. There seems to be a slight sort of gap or difference in the decay rates that are needed to make these theorems true. Okay, so with that out of the way, let's talk about the actual proof. How do we prove this theorem that I mentioned? Let me go back. The theorem at the top of this page. We want to show that if you have E equal length P, then actually E and P both have to be 0. So that The rest of the talk is going to be about how do we prove this theorem. Okay, so let's start with that assumption. Suppose I have a complete asymptotically flat initial data set satisfying the dominant energy condition and E equals the length of P. And again, I need to assume maybe this is a slightly stronger version of asymptotic flatness. But again, in 3 dimensions, this stronger version, it doesn't actually require a stronger decay rate. It just requires having sort of like a little bit more derivatives, like half derivative more to be precise, for this to work. Okay, we're trying to make a variational argument, so we need to use the fact that this minimizes mass among nearby asymptotically flat initial data sets that satisfy the DEC. Well, not exactly mass. It turns out more convenient to say that it minimizes this other quantity. So the quantity is E. So I'm going to take just plain old E and P for to save on notation. Plain old E and P are just going to be the ADM energy momentum of the original data set GK. Okay, so that's the one that is satisfying the equality E equals length P. Now, what I'm interested in is what's happening at nearby initial data. So let's say I'm going to use gamma kappa for any other initial data besides that one special GK. So the special GK is going to be the one where we have equality, and gamma kappa is just any nearby one that satisfies the dominant energy condition at this point. Okay, so then the thing that we could have said that it minimizes, say, something like E of gamma kappa minus the length of P of gamma kappa. But it actually is a little bit nicer to write it this way. So we're going to say that it minimizes E times the energy of gamma kappa minus P dotted with the momentum of gamma kappa. So why is that minimized? Well, it's a pretty simple computation. So you take that quantity, we just get the first inequality. Immediately, the second equality there, right, is using the fact that E equals length P. So I just factor out that E. And then now that's greater than or equal to 0 because of, I'm assuming that gamma kappa satisfies the DEC, which means it satisfies the non-negative mass theorem. So I know that that quantity is greater than or equal to 0. I also know that E is greater than or equal to 0. Okay, so this expression for any gamma kappa is greater than or equal to 0, but then 0 is exactly what you get in the case where gamma kappa is GK. Okay, so this is the quantity that we want to actually look at. All right, so we would like to just see what happens, right, directly from knowing that we're at a minimum here, but there's a complication arising from the fact that although we can view the nearby decaying initial data gamma kappa as lying in some affine weighted Sobolev space B, so I don't want to get into the details of the analysis here, but I just want to say that there is a weighted Sobolev space that captures the idea that gamma and kappa have essentially the right decay for being asymptotically flat. Okay, so we can capture the decay appropriately. The problem is that the space of asymptotically flat initial data, it does not form a Banach subspace because of the additional decay requirements on mu and j. So if you remember last lecture, I kind of emphasized that asymptotic flatness it has 2 important parts. One is that the initial data needs to decay, but then there's an extra requirement on mu and j. So this extra decay requirement on mu and j, unfortunately, you cannot describe that just in terms of a Banach space, right? Not easily, at least, right? So mu and j are these these nonlinear operators on gamma and kappa, and we're just asking them to decay. So it's a little hard to deal with that directly. So enter the Regge-Teitelboim Hamiltonian. So here's the trick. The trick is that we want to replace the quantity that we want to minimize by a quantity that will be well defined for all gamma kappa in the Banach space. So so we can't use this quantity right off the bat because, right, being like, again, this script B just represents decay of gamma kappa. So decay of gamma kappa alone is not enough to have well-defined ADM mass. We also needed that extra knowledge of mu and J. So what we do is let's let F naught X naught be a pair of a function and a vector field on M. We'll call it a lapse shift pair, the lapse being F, the shift being X, such that F naught X naught is equal to EP in the exterior coordinate chart. So in other words, I'm looking for a function that's exactly equal to E near infinity, and then I'm letting it be whatever I want on the inside. It actually doesn't matter. And same with P. Same with X. X, this vector field, it should be exactly equal to P near infinity, but in the compact region, I don't care what it is. Okay, so we'll see why it doesn't actually matter what it is inside, but it does need to be defined everywhere for what we're about to do to make sense. So this is following an idea that was used by Bartnik in 2005 in a similar context. We define this Regge-Teitelboim Hamiltonian, which again conceptually was also a pre-existing physics idea. We take the quantity that we want and then we subtract off this integral. So the integral is F naught times mu minus the product of X naught and J. Now, why do we do this? The point of doing this is that because of cancellation of terms, this expression can be re-expressed as a well-defined functional on B. So as of now, the way it's written, the E of gamma kappa and the P of gamma kappa, those might not be well-defined. And the integral of those terms also might not be well-defined. But the difference, if you put them together, is well-defined. And going back to our discussion from last lecture, you can sort of see why. So, and this is why I don't really care what F naught and X naught are on the inside. So near infinity, right, we have basically that F naught mu term is just a constant E times mu. And if you remember what the original motivation that we gave for E, for the ADM energy is it's exactly those boundary terms that show up when you integrate the divergence part of mu. So the point is, if you rewrite mu in terms of that divergence part plus those quadratic lower order terms, the point is the divergence part is canceling identically. In the limit near infinity, right? The part that when you integrate, there's a piece that looks like from that divergence term is exactly canceling, or approximately canceling the ADM energy of gamma kappa term. And then what's left are those quadratic. So, and I think I mentioned that the decay alone is enough for those quadratic lower order terms to be integrable. So, that's the motivation for why we write this functional down. Okay, so the point is E and P, they might not exist, but integral mu, integral J, those might not exist. But if we look at their differences, then what's left over is always well defined. Okay, but you can't get something for nothing. It looks like, well, if we subtract something off of this thing, then it's not the same functional anymore. And we no longer expect GK to minimize this H over nearby asymptotically flat initial data satisfying the DC because of these new terms. But we'll see that we can take care of this problem while simultaneously handling another complication that comes up. So let's just keep this in mind. So this is our formula for the Regge-Teitelboim Hamiltonian that we're going to use. And now let's turn a little bit of our attention to the mechanics of actually doing the minimization. So keep in mind that we can only minimize subject we're not minimizing over all initial data, of course. We're only minimizing over initial data subject to the constraint imposed by the dominant energy condition. Okay? And the dominant energy condition is a pointwise inequality. It would be a lot more convenient if we were using a pointwise equality somehow, right? Ideally, we would like to use a pointwise equality that defines a Banach constraint manifold, and then we could use Lagrange multipliers, right? Lagrange multipliers is basically, right, you minimize a quantity, in this case a functional, with respect to some kind of equality constraint. So, in other words, we know that we're trying to minimize over everything imposed by everything that satisfies DEC, but we don't have to look at all of those if we don't want to. We can just look at some of the nearby initial data that satisfies DEC. Okay, and so here's a naive solution before we get to the real one. The naive solution to both of the problems that we've outlined is to restrict ourselves to this constrained Banach submanifold, which I'll call C. It's going to be the set of all nearby initial data that has the same mu and j as the original initial data gk. Right? So again, I'm going to just say that plain old mu j, that's the mu and j that corresponds to the original gk. And I'm looking at nearby gamma kappa, but I'm only interested, script C is saying, let's just look at the initial data that has the exact same mu and j as the original. Okay? So this one can actually prove that this is a Banach submanifold because essentially because the linearization of the constraint operator is surjective, but that's on the technical side. Let's just accept for now that yes, this C does cut out a nice Banach submanifold of the full space. Then what we have here is that for any gamma kappa in this C, right, we see that the integrand that appears in the formula at the top, right, that integrand is unchanging, right? If mu and j aren't changing, then that whole integral is fixed for everything in C. So it's a little bit strange because we're defining this functional h on the whole space B, right? But on the constraint submanifold C, there's no difference between this h and just the plain old, E times E gamma kappa minus P times P gamma kappa, just the first part, because the second part is unchanging on C. So that would mean that, again, GK does minimize H over C, and that would be great, and that would be exactly what we need to continue on. But again, it's under the assumption that E of gamma kappa is greater than or equal to P of gamma kappa. And now, unfortunately, with this definition, that's not necessarily true. So the problem is that this gamma kappa that lies in script C, in this constraint manifold, it doesn't have to satisfy the dominant energy condition, and therefore we have no way to conclude that E is greater than or equal to P. So on the surface, it looks like it should because we kept mu and j the same. But even if you keep mu and j the same, that doesn't preserve the dominant energy condition. To see why, just look at the formula, is that the DEC demands, of course, that mu is greater than the length of j, but it's the length of j with respect to gamma. And our assumptions tell us that, well, mu and j are the same as the old mu and j. That only tells you that you're greater than or equal to the length of j with respect to g. So I have the equation, the chain of equalities written out there. So there you see mu of gamma kappa is the same as the original mu. The original GK satisfied the DEC, so this is greater than or equal to the length of j with respect to g. And that's the same thing as the length of j of gamma kappa, but again with respect to g. So this is this sort of, there's this annoying problem, which is that even if you can correctly prescribe mu and j, which is what we're doing with the constraint manifold C, even though you know exactly what mu and j are, that's not good enough to conclude the dominant energy condition because you don't have control over gamma itself. So the length gets messed up when we move from G to gamma. So thankfully we already knew before this the tools that we needed to deal with this part of the problem. This issue can be solved by considering the following modified operator introduced by Justin Corvino and Lanxuan Huang. And that modified operator was sort of followed on work that was used in EHLS in the last lecture. It was used to prove the density theorem. So some of that same work that was used to prove the density theorem was sort of streamlined in this work of Corvino and Huang to come up with this modified operator. So what's this modified operator? We're modifying the J. So the J operator of gamma kappa is just going to be the modified J operator is the old regular J operator, but now plus this other term. Oh shoot, there's a typo in here. That second gamma shouldn't be there. So it's 1/2 gamma sub ij, G upper GK, and then J sub J. So that last J sub J, that's the J corresponding to the original GK again. And so sorry, that's that second gamma, the gamma that's right before J, that one shouldn't be there. That was an accident. Okay, well, this operator J bar, the thing that we added to it is, it's just some simple 0th order stuff in gamma, right? So it doesn't really change that much about the analytic properties of J. But the purpose of the extra term is that if the J bar of gamma kappa equals the J bar of GK, then the G length of J is actually greater than or equal to the gamma length of J of gamma kappa. So this is exactly the missing ingredient in the inequality above, or higher up in the page, right? If we were using J bar instead of J, then we get exactly the inequality that we want. Okay, this motivates us to modify our definitions as follows. So, and I put in red exactly the changes we had. So you take the Regge-Teitelboim Hamiltonian that we had on the previous page and just swap out that old J for J bar. And then this will give us the modified Regge-Teitelboim Hamiltonian. And similarly for the constraint, instead of asking for J of gamma kappa to be J, we ask for J bar of gamma kappa to be J bar. All right, so now every element of C bar does satisfy the dominant energy condition. That was the whole reason why we made the change. So now we can make that argument that we wanted to make before. So we can conclude indeed that GK minimizes this H bar over this constraint manifold C bar. And so we, as I said, we want to use some infinite dimensional version of Lagrange multipliers. So in finite dimensions, right, let's just quickly recall what Lagrange multipliers would say. It says that, the gradient of the functional H bar is spanned by the gradients of mu and J bar, but mu and J bar thought of as functionals on the space B. So what's the Banach space version of Lagrange multipliers will tell us. So those Lagrange multipliers correspond to a lapse shift pair, which I'll call F1, X1. And the important thing is that we actually know that they decay to 0 at infinity. That will be important to us later on, such that for all first order variations, HW of the initial data, okay, we have the following equality. So this is the linearization of the functional h. So that's kind of like in finite dimensions, that's like the gradient, right? So it's the linearization of that on HW is equal to the 1 over 8 pi is just a normalization. And then integral of, and then I take f1 times, again, the linearization of mu minus x1 dotted with the linearization of j bar. Okay, so the linearization of mu and linearization of j bar, those are like the gradients of mu and j. And integrating against f1, x1, that's kind of like this comment about span, right? Except it's infinite dimensional, right? So these Lagrange multipliers, instead of just being individual numbers, it's like a whole function's worth of numbers. So this is, if you kind of just think about it, this is a reasonable analog of sort of your classic Lagrange multipliers. All right, so at the top of here, this page, I just having the same equation I wrote on the previous page. So it's saying linearization of h bar is given by some integral of f1 against the linearization of mu minus x1 against the linearization of j bar. And then, well, we can just take the adjoint operators to rewrite this in terms of the adjoint linearizations. Okay. Meanwhile, we can also compute the linearization of h bar directly from the definition. So here I'm just reminding you what the definition of h bar was, right? So this is our definition of h bar. And then if we linearize this, then actually we get a very similar looking formula as above, except that now it's the adjoint linearization of mu against taken on f0 minus the adjoint linearization of j bar applied to x0. And so I don't want to get too deeply into this, but I just want to give a sense of why this is a very reasonable formula, because what's happening here is, so when we try to linearize this expression, right, the idea is that we'll get the d mu, but we want to take the adjoint. When we take the adjoint, we have to worry about the fact f0 and x0 do not decay to 0, right? f0 and x0 are actually going towards constants. So that means when you take this formal adjoint of d mu, there's a boundary term. And what we learned sort of from our previous lecture when we talked about the motivation for the definition of ADM energy momentum was essentially that when you take the integration by parts procedure, the boundary term that you're going to get from f naught times d mu is exactly matching the energy. So that's kind of why this comes out this way. It's not like it's not a coincidence, and it's not luck. It's actually just, this is what it is because all the definitions are essentially set up to make this happen. Okay, so now if we put these two things together, right, what you see is that saying that these two computations together, you see that that the sum f naught plus f1 and x naught plus x1 actually solve the adjoint equations. So so this last bullet point is explaining, I think, what I had said in what I spoke out loud, which was that the reason that this computation works because EP are essentially defined to mate so that it will work. Okay, now it says since HW, I think I meant to say since HW is arbitrary, setting fx equal to the sum of these two things, we see that this new combination, this sum, will actually solve the adjoint equations, and you get 0. So now let's summarize what we have up to this point. The variational argument yields the existence of a solution to the, I'll put it all together in one jumbo equation. It's the linearized adjoint equation, or the adjoint of the linearized equations. So it's a big system of equations. And not only do we have a solution to this solution is asymptotic to E and P. Like, right, because it's F0 plus F1. F1 I said was decaying, and F0 was basically equal to E naught. Sorry, it was equal to E in the end. So I have a solution, and that solution it has this asymptotic. So from here, actually, now it follows from work of Baig and Kruschel, who've proved that this is impossible if E equals the length of P and is strictly greater than 0. So what I want to do now is I want to outline that proof a little bit. Assuming GK satisfies this slightly stronger asymptotic flatness condition. Something that's interesting about this is the proof does not actually require fx to be a global solution. So we worked pretty hard to get this this global solution, but this part of the proof only has to do with asymptotics. It only uses the fact that the equations hold asymptotically, which sort of makes sense because we're just talking about some asymptotic quantities here. In particular, this is one reason why swapping out the j but for j bar, it doesn't actually hurt us, because it turns out, I mean, we only want, like, there's nothing magical about the exact adjoint equations for when it was just j. So changing it by j bar, it doesn't really change much, because again, asymptotically, those quantities are pretty much, these equations are pretty much the same. Okay, so assuming only the fact above and that E is not 0, and let's rotate our coordinates so that P equals 0, 0 length P, we can actually show what the asymptotics look like just by some computation. You can see that this lap shift pair Fx has to be, again, they have to be like, essentially have like harmonic type asymptotics. So F is, you can see E minus some term over R plus some other terms. X is, again, the first two components essentially mostly 0, and then the last one, again, something P minus a term over R and then plus other terms. So it's a little bit annoying though, because I wrote other terms. I did not write lower order terms because they're not lower order. The other terms actually do not have to be lower orders, but so they are kind of important, but I don't want to get bogged down in those details. But this is a potentially interesting set of equations for the lap shift, perhaps, because it's more general than the situation where E equals P, right? This holds anytime, as I said, anytime you have a lap shift pair that asymptotically satisfies the equations at the top of the slide. Okay, now, how do we get a contradiction? So the last step is subtle. So now let's assume that E equals P and it's not 0. Then the asymptotic expansion that I gave on the previous slide, and then working more with the adjoint equations that we have, you can actually construct a vector field that is at most order r to the 1/2, and it's the third component vanishes. So it's a vector field, but it's really only a vector field, with the first two components non-zero. And we can show that satisfies we're talking about asymptotics, so the Euclidean divergence of this vector field is E times essentially the radial coordinate to the 4th power in just the first two variables, so the xy variables. But then r is the radial coordinate in all three variables, r to the -5, then plus lower order terms. So the upshot is that if you think for a while, it's hard to imagine a vector field with such behavior, and indeed one can prove that it is impossible to have such behavior. It's just you can't have a vector field like this. and that's the end of the proof. So I just want to say that this last step is the one that requires a faster decay rate assumption in dimensions greater than or equal to 5. So this is really the one step where that causes the issues with decay rates. And I think, when we first saw this, we pretty much believed that it was probably just an artifact of the way the proof works, but it wasn't until I guess we sort of found those the counterexamples that we mentioned that we realized that, oh, this is actually a significant step in the proof. Anyway, if you're listening to me now, definitely thank you for sticking with me for this entire series, or at least this entire lecture, and I hope that you enjoyed this series of talks. Thank you.